The speaker this afternoon's special guest seminar is Gilles, who's going to be talking on the v-Picard group of Stein spaces.
Thank you, and thanks for the invitation to speak here. So I would like to explain a computation that we did with Ertl and Niziol. So we were interested in the co-kernel of the map going from the analytic Picard group to the v-Picard group for Stein spaces. But first, let me explain the setting. Okay, would be a complete discrete valuation thing with fraction field. Okay, and perfect residue field small scale. And I will take C, the completion of an algebraic closure of K, and X will be a smooth analytic variety over C. So when we have this homology variety, we can define our X various topologies. So we can define the analytic topology. We also have the entire topology, and if I write with diamond, the associated diamond, this is the same. We can also define the proétale topology, and we also have on the diamond, the associated diamond, we also have the V topology. So this is generated by open covers and surjective maps of affinoids. And we want to compare the, so if I write VB of X tau or tau, one of these topologies, so this is the category of locally free or finite modules.
So for the proétale, I think, do you use the version in?
The completed. You mean for the structure shape?
No, for the proétale, the first version, that is the one of Scholz's paper in 2013.
The flattened.
Or the kind of more.
No, the first one.
The first one. Does it matter? I think it shouldn't matter in all known cases.
I think in the computation we need the flatten.
I think it in Heuer matters actually.
Sorry, matters in the sense that it goes into the proofs or the category changes?
No, he uses essentially that is the first definition. Is that correct?
Yes.
But the category is the same, right?
No, so no, the others proétale which are inverse limit with finite time.
No, the category of vector bundles
should be the same.
Yeah.
Not the site, yeah. I agree that the site is different.
The category, yes. Yes, and so we want to compare this, and yes, and more precisely, here we are interested in the Picard group, so Picard, so X, so the group of isomorphism classes of vector bundles, and I will take here vector bundles of from 1. And the first thing is that if X is affinoid perfectly, and then all the notion of vector bundles are the same. They coincide. So this is a result of I knew. And since the proétale topology and the V topology, they are locally affine perfectoid, this means that for any x, we have an equality between the two categories. So for x. And so here we are interested in the map. So going from the analytic Picard group, this is the same as the Ertl Picard group. And then we have this map to the proétale Picard group, which is the same by this as the V Picard group. So this is injective, and we are interested in the cokernel of this map. And so we use here the results and construction of Heuer. So it defines a morphism.
So you are in mixed characteristic, because otherwise
Yes.
you have some perfection we kill things okay.
And thank you. So it defines a Hodge-Tate logarithm from this v-Picard group to the omega-1 x twisted by -1. So this is the Tate twist. And using this, such that we have an exact sequence like this. So this is exact. And we proved that first this H log is surjective. If X is proper, so smooth and proper, it is everything is P. Okay. And it also proved that if X is the region affine space of dimension D in any dimension, we have that the image of the H log is given by the omega-1 by the closed differential. And this is use the computation of the periodic vital cohomology of A. Which is due to Niziol. And alternatively by Bloch-Kato. And here we want to extend to all smooth Stein spaces. A Stein space is an increasing union of affinoids, say xi, such that the compactification of the Heuer compactification of xi is inside xi plus 1. And in particular, the affine space is Stein. And so we have this result. So I forgot this. We also, I will explain, but in fact, the H log we can define it in any degree. So H log I for I bigger than 1 to H I B X or to omega I of X. What means I? And so we computed, in fact, the image of the H log in any degrees. So X Stein and smooth. And in fact, we need to restrict. So I will define U as the group of principal units or cross. So this is principal unit. And we have that we have an exact sequence of abelian groups. So as expected by this computation, the closed differentials are in the image. But we have more. So I will write U here, and this is, I will write that. And here we have some questions. For the HT log IU, this is the restriction to the subgroup U. Omega I. So here the map, I will call it X, and X, this is the Bloch-Kato exponential. From the work of Columbus, Niziol. And in fact, here we are using the construction of Bloch. This is from omega I omega I X mod curly minus I to the proétale cohomology, the p-adic proétale cohomology. And now this group, so this group is inside the p-adic proétale cohomology.
So is this injected, the exponential? Yeah.
And this is the intersection. This is the differential that maps to the integral cohomology. So I of X, maybe I should call this I. This is the intersection of the image of the Bloch-Kato exponential and what I will write, delta I. Proétale is the map, the natural map from the integral cohomology. So since it is Stein, for the integral cohomology, Ertl and proétale are the same. I should write this one. So if we assume, I will make a remark in a second, but if for the moment we assume that the image of the Ht log restricted to U is the same as the image of the Ht log, we have that so this cokernality contains the closed differentials, but we have more. We also have all the differentials that comes from the integral cohomology.
What do you mean by here Ertl and proétale cohomology with ZP? So one of them is the different version of the proétale set that they give the same. And what is the Ertl x ZP?
It's the limit.
It has a naive limit without lim1. You mean just the naive inverse limit or
No, the derived.
the continuous cohomology?
The continuous cohomology.
But then you
For
don't,
fine spaces, this is the same.
but why you need Stein for it to be the same? I think for Z mod P to the cohomology, you have this, it's always the same on everything. I mean, on any reasonable. Okay.
Maybe. For Stein, it is the same, but I don't know if in general it's the same or not. I don't know. Okay, a few remarks. So first, yes, here I am only computing the restriction to U, and later in the talk I will give examples. And in all my examples, we will have an equality. I mean, at least for one U and M of the H log. One. I don't know if it is true in general or not, and I don't have an example where they are not the same. So in general, I don't know. We have an inclusion, but I don't know. And the other thing, yes, this group I of X can be non-trivial. So it is the case, for example, for the disk of dimension at least 2, the open disk. So the I1 of X is non-zero. So we have differentials that maps to the integral cohomology. And we recover the results of Heuer. Because for if X is the affine space, the H2 of XZP is 0. You can see that by comparing the analytic cohomology to the algebraic one. So the group I1 of X is 0. And if X is a curve, then the H2 proétale the rational H2 proétale is 0. So,
You mean
Stein.
Stein curve,
Yes.
but he proved it for all curves, not necessarily Stein.
No, yeah, the result of Heuer is true for all smooth curve.
So all smooth without any hypothesis of like adding locally finite over just adding, or you need some I don't know, like what about non-quasi-separated? I don't know.
Smooth, I have separated it.
What?
Smooth, for me, smooth means separated. Okay, so to the proof, I need to explain how this HT logomorphism is defined.
I have a question. So if X was proper, I guess this statement as written is also literally okay, because the map is surjective and the term on the left is everything. But my question was, is there a version of the theorem which sort of combines the proper case and the Stein case?
I don't know, because we have this.
Like the statement as written, could it be true for something that's like product of a proper thing and a Stein thing?
Partially proper maybe.
I'm thinking something like affine space over something proper, but
We don't have a good comparison theorem of the type we are using here in that case, so maybe one also have to work it out. In fact, this is something that we got stuck with Pierre on, so to extend this kind of things to partially proper. Maybe for the product it's going to be printed off.
So the Hodge-Tate logarithm. So first we have this theorem of Schulze. Yes, maybe we can work we can work on the proétale side and on the V side. This is the same, so I will mainly work on the proétale side. So we have this this new from the proétale, and this is also true for to the proétale side, and we have the Hodge-Tate morphism between the Ri of mu to this is an isomorphism with omega I minus I for all I. And LC is smooth. So we have this H2 morphism, and then if we use the Lorentz spectral sequence, so for this new or the invertible functions, so this computes the HI of X RG, or you get the proétale cohomology. And so the first term of the spectral sequence, it will give this an exact sequence. Here we have the H1 eta of X. Then this goes to the H1 proétale of X, and here we have the motion to the H0 eta of X R1. And then here we can use the exponential map to get an isomorphism to R1 of O. And this is using the Hodge-Tate morphism. This is just the H0 eta of X omega 1 minus 1. And the in degree 1, the HT morphism, and the HT log is this morphism. And you can do that for, in many degrees, more generally. To H, right? But in fact, in the case of Stein spaces, this can be made more explicit. The Hodge-Tate morphism. So we have an alternative. For the definition of H3 of Stein spaces. So I will. So first, a remark. Since X is Stein, we have that Hi beta of X omega j. This will be 0 for I bigger than 1, and so the H1 eta of Rj mu O is 0 for I bigger than 1. And so this gives an isomorphism between Hi proétale of X0 and the H0 eta of X R I to the omega I X minus I, and this I will still call it Hodge-Tate.
So could I ask a question with the previous diagram? What is the exponential map from O to O cross?
Yes, so this is defined.
I know what it is from O plus, but
Yeah, if you're close enough, but in any case, since
The R1 is the same for.
Yes.
oh, that's the okay.
Yeah, but we need the R. I is bigger than 1 here.
so O star is the V shift, so the kernel of multiplication by P is mu P, but this is this is trivial. So this is divisible. Star 1 euro star, so you can define the exponential, but why is it an isomorphism? This is one of the
You can compute the the kernel. You can compute. You have this over bar, which is over mod this u,
Yes.
and you can compute this this the cohomology of this this shape.
Right, this shape is like its own push forward, right? But
Yeah.
the higher direction will just vanish.
The higher.
Yeah, the higher cohomology of this will be 0.
Okay, that's 1 point, and also that it does not.
Right, and the Ertl is the same thing.
Okay, okay.
Okay. Yes, and note this, we can define it using the cohomology of Biedermann. So we have the sheaves Biedermann plus 1 Biedermann. On the point-hand side. And we have the usual map theta, which gives an isomorphism from this to 4. And so this is a work of, so in the affine space, this is 2 over R, and in general, to both flow. We have that if X is a Stein space, first we have that if Y is a Stein space over K this time, and X is the base change to C. And this is also true if Y is the graphenoid. Then we have that the cohomology of Biedermann X Biedermann plus mod T can be computed by the complex. So here we have O of Y, tensor C, and then here we have the omega 1 of Y, C minus 1. This is of dimension D. This is 0 and omega D tensor C. And in fact, even if X does not come from Y, this will give a map. So if X is directly defined over C, we get a map, and it will be an isomorphism in fact. That I will call V. So this is proved using the proétale map. Due to Schwarzschild. So we get an isomorphism from the proétale map between the H I proétale X Biedermann plus T and 2 omega I of X minus 1.
Gilles, what is the middle block?
It's a solid. I work in the solid K vector space.
And the differentials are here?
Yes.
Interesting.
So we have this, and And we have the following compatibility. Sorry, wait, okay, right. We have a commutative diagram. Using this, so we have H proétale X all cross. Here we have the H dimorphism to the omega I. And
O cross or
sorry, O. And then here we have theta with H I proétale X federum plus. And here this is this Poincare lemma.
How do you view a dagger affinoid as defining some X over C, which was the usual space?
Sorry?
A dagger affinoid is not exactly usual space, it's before you work.
Yes, but you can still compute.
You can define proétale cohomology.
Okay, you can define all the notions of. Okay.
It's just to compute the proétale cohomology of. I am using this to compute the proétale cohomology of Stein spaces when they are defined over C.
sorry, what is the relationship between the two?
In fact, we need, this is not enough to know for Stein spaces over K. To have the result over C, we need also the results when for dagger affinoids because we use a Stein covering.
So is there some approximation statement that things inside X can be approximated by things over K? I'm just trying to follow.
Of a finite extension of QP.
Is it omega IX minus 1 or minus I?
It's minus.
Yes. Yes, you can read minus.
The isomorphism is called PL? No.
Yes, for Poincare lemma because it comes from. Okay, so this was for the Hodge-Tate logarithm, and now I will explain the Bloch-Kato exponential. Okay, so we have the length. So as I said, this is due to coordinates that's been as Niziol, and here we are using the construction of both floors. X evaluation. And we have a mark of exact sequences. So we have the omega I minus 1 of X and multiplied by V. And we have this X with the proétale homology, the proétale homology. And here we have so this Hodge-Tate term So this is defined over F preve, and F preve is the completion of the maximal unramified extension of K. This and B semester plus at. So this is just the banner version of the usual B semester. And here the Hodge-Kato cohomology. So this is a refinement of the RAM cohomology, and acting on this, we have a Frobenius and a monodromy operator, and we take the eigenspaces, and the Hodge-Kato cohomology, when we extend the scalar to C, we get the RAM cohomology. So here we have a map to the RAM cohomology.
What tensor product over what?
F breve, this is the completion of maximal unramified extension of K. So here we have the omega I of X, the kernel of the differentials, and here we have the same thing. And, let me explain how this is defined. So construction of X. We start from the fundamental exact sequence of periodic Hodge-Tate. So this is QP. Here we have B, 1 over T, Y is 1, and here is goes to be the RAM not be the RAM plus. So this B here is just the period shift that is given by the section on the part contained curve. I mean before quotiented by 5. So we have this, and we take the cohomology. So the proétale cohomology. And we get a map from H I minus 1 proétale X be the RAM by be the RAM plus. HI of Q plus. And in fact, the work of Lebrun and Bosco, we can using again the Poincaré lemma, we can also compute the cohomology of this. I will not, so I will just say, so again, this is by computation of at Bosco. We have a surjective map. By from this H I minus 1 by X. So this is again using the Poincaré lemma. So this, there is a shift. I minus 1 X over B minus I. And so to have this X map, Bosco shows that this can be factorized through this pi. So here we have pi. Minus 5, and this, and the x is this. And we have, we could also, if we start with this exact sequence, but twisted by 1. So if we start with the same, B, we get this connected mechanism that I will write E Peterson plus H I minus 1 proétale of Peterson plus not T to H I proétale of P1. And this is compatible with the X. So we have this compatibility. Also, we have a commutative theorem. So the quotient homology of X, no, sorry. Omega I X minus I, here we have this X, maybe twisted by something. I plus 1 quotient of QP1. And here we have this connected mechanism. And here we have the cohomology of P1 plus. So we have this, and now we can, with these two propositions, we can prove the two of them. Yes. It's and you know. So we start with the map of exact sequence. So this is so we have this view. This was the principal unit, and then the log. And this we compare with the fundamental exact sequence. So this. A bit of this. And I will. And if we take the cohomology of this, and we use the the two propositions, the compatibilities with all the map. We get a commutative diagram. So here we have the proétale cohomology of this U. So this corresponds to the first line, the first exact sequence, omega I. Here we have this is the connecting morphism of this first exact sequence, and then we have the H them to HI plus 1 proétale QP mod ZP. And then here we can go to this quotienting by Kirby. Here we have the X map. One. And here we can compute the kernel. This is the integral cohomology. And so this first, the row is exact here. And the column here is exact. And so now, I mean, this gives the result because so here we have the HT U. And we directly see that the kernel of the differential is inside the image. And then you can see using the exactness here that the quotient is the differential that comes from the integral cohomology. And to finish, I would like to explain a few. No, first I will make a remark. Oh, I shouldn't have. If we use this exact sequence here and here this is omega I minus 1 x mod PLD. And if we define I tilde, the difference. We define as the here but we back to here, and here we have the integral cohomology. One I should take minus dpi. Mod G, so G is the maximal Hertzsche subgroup. This here, we have the same thing. I will just write this as HI. So if we define this I tilde this way, we say that I will call alpha. So we say that we have a surjection from I tilde to I. And we say that if alpha is injective, and then I tilde, and so I is 0. And in fact, this Bloch-Kato part of the p-adic cohomology, it behaves like the L-adic cohomology when L is not big. So it kind of contains the analytic information of the p-adic cohomology. And so this means that this I of X, it comes from, I mean, it is a p-adic phenomena. And so I can, just to finish, I can give a few examples. First, if X, so if X is the affine space, this was already done by Heuer. So in that case, we have that the analytic Bloch-Kato is 0. And we also have that the Random cohomology is trivial in higher degrees. So for I. And so this gives us the HK I is 0. And we also have the comparison with the case. We also have that the integral cohomology is 0 in higher degrees. And so we get that using this, we get that the I of X is 0. And in particular, this gives us the v-Picard group of X of the affine space is the omega 1 X is equal to 0, twisted by -1. And we can do the same for the torus. I see. So in that case, we still have that the Picard analytic group is 0. The Random cohomology is not trivial, but it is finite dimensional. So this is the product of, so this is over C, D. And we can use that to compute that the HK I. This is just the product of QPD. And again, by comparison with the algebraic case.
So I think that you looked at this cohomology of the principal units to define the.
Yeah, in all this example, we have a surjection from the H1 X U at the H1 X O star. And so this gives an item of, I mean, we have an equality between the image of the HT log and the HT log restricted to U. In all the examples I am doing here.
Okay, but this is
I don't know if this is true. I don't have an example where this is not true. And I don't know if this is true in general. So here we have a product of CP. And so we get that this is injective, and using again this map, we have that the I X is 0, and we have the same results here. And just one last, so this can be generalized to any analytification of affine smooth algebraic varieties, because in that case we have comparison theorem between the integral cohomology, I mean between the p-adic cohomology and the Hodge-Tate cohomology. So this alpha map will be injective for any analytification. And just one last example for the Greenfeld space. H dk. This is the projective space, and we remove the k rational hyperplane. And for this, we also know that the analytic Picard group of H is C is 0, so this is due to Heuer. So we know that the RAM cohomology, this was computed by the pendulum H. So this is the generalized Steinberg field by the right, like that. And we take the dual. Nice. And so here, this is the generalized. The locally, local, this is locally constant function. Yes. And we also know what is, so we get that the HKI, this is the dual of the Steinberg of Q, P. And we also have that the integral cohomology, this is the dual of the Steinberg of ZP. So this is due to Gomez de Spinesco Niziol. And so using again the same remark, we get that this I, if that the I group is 0, and this P H C D, this will be the omega 1. The closed differential. Okay, I will stop here. Thank you.
Further questions?
Can you deduce a sense of correspondence in some cases from relation?
I don't know if we have a good splitting of the. I mean, even in the case where I of x is 0, so when we have just a closed differential.
Right, then it's kind of right.
Yeah.
I guess for what I'm asking, you would have to have JI to be non-zero. Right?
And
we will form.
I think it could give one. We could, but I don't have a nice splitting of the HT logarithm.
No, I was asking if there's maybe not a very technical, but still a way to lift the will form.
Yeah.
So the Simpson's joke class would be there.
But I think it's never 0.
But maybe sorry, I should have asked when restricted to some variety. I think you're saying it's never 0 even for Stein.
Right. It's non-zero for a disk.
Right.
So
what is non-zero?
The class of the Simpson germ.
There was this map from Picard to one forms.
Yes.
Simpson germ is split if and only if the Liouville form of the cadential bundle lifts along this form. But sorry, this is a big question.
I wanted to ask where for some clarification exactly where the Stein hypothesis is used. I saw that it was in this result that you quoted Gomez de Spinesco.
Yeah, we need to be able to compute the periodic cohomology.
So it's in that result. This result, I mean, it's used in this result of Gomez.
Yes.
Is that the only place that it happens? So some control.
But maybe to check the compatibilities, to have this commutativity, I think to have the commutativity at the end, I mean, to check that all the maps are compatible, we are using that we have this nice, that we can write the HTML because I'm using this logarithm.
Oh, you use that description.
Maybe we can check the compatibility. Maybe it's still compatible. All the map that yes, but we do not have a Bloch-Kato exponential. I mean, to compare to periodic proétale cohomology.
Yeah, so if you take partial property, for example, you still have derived comparison, derived sequence, right? But it's not clear what is objects on the left, how this mapping to this here, what is this kernel? And here the kernel is this nice form using the differentials, but in general, we don't know what it gets into.
So the assumption that you work over the completion of a discrete, the algebraic laws of the completion of the discrete valuation ring, this is for approximation arguments to approximate, to define the Hodge-Kato cohomology. I mean, what happens for C arbitrary algebraically closed field? How much of this?
I think this has these two.
Our techniques don't apply for C.
But we do not have this computation or NEC.
And it's not possible. Is it possible to extend these kind of things to finite union of Stein? Just for Bhagat's question earlier.
Place which can be covered by
Finite union.
It's already difficult for two. So.
Yeah, actually, we failed for two.
You can only do three. There's nothing further, that's thanks to Legend.